Hello, welcome back to Chapter 9, Nuclear Radiation. We are going to discuss nuclear equations, and hopefully to this point you've really studied and looked at your chart, and you know your radioactive decay species, your alpha particles, beta, positrons, neutrons, and gamma rays. You'll need to know the symbols for those, and charges, and masses, and all of the above. Okay, in a balanced nuclear equation, that we are dealing with nuclear radiation. So particles are being emitted from the nucleus. And this is a huge difference from what we've studied in Chapter 5, because our mass number and our atomic numbers are changing from one side of the equation to the other. So we are ending up with different elements or different atoms on the other side of the equation. But the idea that everything has to be balanced is still the same. And here we're going to have to balance mass numbers and atomic numbers. So if we look here, we want to remember that our mass number is, trying to get my pen here. Okay, the mass number is this number here, so it's this superscript, and this number here is the atomic number. The atomic number is the number on the periodic table that identifies an atom or an element, and it is the number of protons that are in the nucleus. So this is the identity of an element, and as we see, this can change from one side to the other. But what stays the same is the mass, the balancing of the mass number and the atomic number. So we have 251 as our mass number on the left-hand side. So these are our reactants. We have our arrow saying equal to the mass number of our products. So if we add up 247 and 4, we get 251. So both sides have 251 as the mass number. Atomic number, we have 98. And on our right-hand side, we can add up 96 and 2, and we get 98. If we're given an incomplete nuclear equation, first we have to write it out as incomplete. You can put a question mark or a blank, whatever we're trying to find. Then you determine the missing mass number. Then determine the missing atomic number. And from that atomic number, since that's the identity of an atom or nucleus, you can look at your periodic table and you can determine the symbol. So if we look here, we've got, this is an alpha particle emission. Keyword emit means that the alpha particle, which we know from our chart looks like a helium nucleus, it's emitted. So that means it's going to be on the product side of the equation. Okay, later we'll look at if you capture a particle, and that's going to be on your reactant side. Okay, but emit, think about emitting across this reaction arrow, it's going to be on the product side. Okay, and this is just an example of a balanced radioactive equation. Okay, its first question is, write the equation for the alpha decay of radon-222. So first we know we can write out radon-222. That is the mass, this is our mass number. We have to know that the alpha particle looks like the helium atom. And if it's decaying, that means that we're going to be we're emitting helium to the product side. Okay, we don't know, we've got to have it balanced, we don't know what our nucleus is there. And we know that if we find radon on the periodic table, that it's going to have an atomic number of 86. That's where this number comes from. You go to your periodic table, and it's understood that you know how to go to your periodic table and find the atomic number, which is 86. Okay, both sides have to balance. So our mass number is 222, and on this side we only have a mass number of 4. So we have 222 and we have 4. So in order for our product side to balance with our reactant side, we're going to have 218 as our mass number, because 218 plus 4 gives us 222. So be sure you don't do it backwards. Be sure you don't try to add 4. Okay, you want it to balance it on the side of the 222. Okay, when you are determining the missing atomic number, you do the same thing. So we have 86 and 2, so we know we have to have an 84 here. 84 plus 2 gives us 86. So your atomic numbers and mass numbers have to balance the total on your reactant side with the total on your product side. Once you find the atomic number, now you know your symbol, because the atomic number is the identity of the nucleus. So you go and you look for 84 on your periodic table, and you see, as you move across, you should find exactly what is here. Okay, and so then we just write the complete equation. We found our mass number on the previous slide to be 218, and our atomic number to be 84. And then we can check it. 84 plus 2 equals 86. 218 plus 4 equals 222. Now we're going to look at a beta particle emission from the nucleus. And this is going to be very similar how we balance these. This is an example here, and it's showing a balanced equation. We have 0, so we have to know what our beta particle looks like an electron. So if we were asked to write the equation for the decay of 42 potassium, 42 is our mass number, and we look for potassium on the periodic table. Our atomic number is 19, so that's where we get this. We're decaying this sample, so we know that means go ahead and draw your arrow, and you're going to form, we're not sure, plus and beta emitter, because we emitted the beta particle. So we have to know that what a beta particle looks like. Okay, so now we determine the missing mass number. We have a 0 here, and nothing here right now, and we have 42. So we know that 42 plus 0 equals 42. So our mass number is going to have to be 42, just like it is on the potassium for its mass number. Then we have to determine atomic number. Okay, this is where we have to know to have a negative 1. Okay, we have to have 19 as our total atomic number. So we're going to have 20 for our missing nucleus, because 20 minus 1 equals 19. So we've got to have 19 on both sides. So if we go and find 20 on the periodic table, we find calcium. So that is our nucleus, has an atomic number of 20 and a mass number of 42. So if we check the equation, 42 on our left side, 42 plus 0 equals 42 on our product side, 19 and 20 minus 1 equals 19. So our equation is balanced. We can solve for positron emission the same way. We're just going to look at this. We're not going to necessarily go through and do this one. We'll do some more practice at the end. But a positron is, first you have to just know that your symbol for this particle is basically the opposite of an electron, or it's got no mass. It has a positive 1 charge. So the positive charge versus our beta particle has a negative charge. And so if we were to be trying to find this missing link here, we know that it would have to be 24 as our atomic number. Okay, so if we find 24, it matches up with chromium. Okay, because 24 plus 1 equals 25. And 49 plus 0 equals 49. So we have to have a 49 also on our product side. We can do the same for gamma radiation. This one's very simple. If you emit gamma radiation, so you're emitting it on the product side, you have no mass. So there's 0 mass and 0 charge. This is why this is super penetrating. There's no mass to slow it down. Really, the heavier the particle, the slower it is. And so all that we do is denote an M there, which basically means the energy is being emitted from this unstable nucleus. And this is indicated by the M that follows the mass number. But our symbols in our nucleus here stays the same because we have a zero mass, zero charge, so it's different from our previous examples. We can also look at an example of radioactive isotopes that are produced when a stable nucleus is bombarded with a radioactive nucleus, and this is called transmutation. But we will balance these just the same. It's just that we're going to have a particle over another particle on our reactive side. But we still have to balance just like we would normally. So if we have 99 as our total, 98 plus 1 gives you a 99 mass number and an atomic number of 43 plus 0 of 43. Okay, if we emit, we're releasing an alpha particle. Okay, this 43, we got this from the periodic table. If we go and we find our TC symbol, it's a 43 atomic number. Okay, and so on our product side, we only have 4 and a 2. Okay, so we have to make these match, of course. So in order for these to equal each other, our reactant side and our product side has to equal. We have 99, so we know that our mass number is going to have to be 95 because 95 plus 4 gives us 99. So now they're equal. For the atomic number, we have to basically subtract 2 from 43 because 41 plus 2 equals 43. So this equals 99, this equals 43. Both sides have to be equal. Our atomic number is going to be 41. So we find 41 on the periodic table. So I'm just going to rewriting the whole thing. I'm going to get the symbol in B. And we're going to have a 99 there. So if we look at, make sure everything's balanced. So, we're going to have a 95, a total of 99. We have a 95 there. So 95 plus our 4 of our helium gives us 99, which we have 99 total on our reactant side. We have 43 total on both sides, 43 plus 0, and 41 plus 2 equals 43. On some of the extra practice that I uploaded on Blackboard for you, we have some examples where you'll see capture instead of emission. Okay, and earlier in the presentation, I'm just going to remind you of what capture versus emission means. But emission we've seen throughout the presentation where we are emitting that alpha particle or that beta particle or gamma or whatever the radioactive particle is to the product side. Okay, if you were to capture the particle, all this means is that that particle is going to be on your reactant side. So you're capturing it in order for you to produce your products. So if we were going to look at the beta capture of beryllium-7. Okay, so our mass number, so we put that down here. We go find the E on our periodic table, and we should get 4. And we have a capture of a beta particle. So we have to know that a beta particle is this. Looks like an electron. Okay. And then from here, all we do is the same. It's the same idea. We add up our mass numbers and our atomic numbers. We have a total mass number of 7. Okay, so we know that we're going to have, we have nothing on this side because we're capturing and we're going to produce a product. We know it has to be 7 here. We have 7 plus 0, and we have a 7. We have 4 minus 3, so we have a 3 as our atomic number. And since we have nothing on our right-hand side, our product side, if we go and we find 3 on your periodic table, this corresponds to lithium. And so it's the same idea, the same balancing. It's just if you have capture, you're capturing the particle on the left-hand side and going to produce the nucleus and not release a particle to the product side. There are plenty of examples for you in Blackboard on mastering chemistry, but these will hopefully help you, especially with any that involve capturing. Your book doesn't get into that very much, but these will help you with the extra practice. But thank you, and I will see you in the next video.